Thank you very much, Vincent, for the kind introduction, and thanks a lot to the organizers for having me here as a presenter of this nice seminar. I really appreciate it. So my name is Martin Esmann. Until very recently, I've been a postdoc at the Center for Nanoscience and Nanotechnologies with Daniel Anzilotti-Kimura. And since a month ago, my current affiliation is the University of Oldenburg in Germany. The topic I would like to present is the inelastic interaction of light and sound in tailored multi-layer devices, so Brillouin scattering. And in particular, I would like to address the question how we can exploit certain topological properties of these multi-layers in order to make the Brillouin scattering itself inherently robust to certain types of spatial disorder. To put this idea into a bit of a broader context, let me briefly remind you that, well, the research field that we are mainly concerned with is nanophononics. That is the field where we are trying to tailor and control the confinement and propagation of phonons in the gigahertz up to terahertz regime, with the idea in mind that these phonons essentially couple to any other excitation in a solid state body that explicitly depends on the relative position of the atoms in the lattice. That is, electronic properties, optical, magnetic, or thermal transport properties could all be subject to coupling to these phonons. That is, one could target controlling these excitations using sound. That is, in essence, we are aiming at a paradigm change from seeing these high-frequency acoustic phonons just as an unwanted source of noise and decoherence towards identifying them as a useful resource in certain situations. This is quite an abstract statement, yet there have been successful implementations and devices in nanophononics. Let's say since the last 20 years or so, there has been quite tremendous progress. And a lot of these devices are based on one-dimensional superlattices. That is, to give you an idea of what I'm speaking about, let's consider a superlattice composed of alternating layers of two acoustically different materials, such as gallium and aluminum arsenide. By stacking these layers in a periodic fashion, one introduces an additional periodicity that, in case-based, is related to a new band structure, with bands of allowed propagating modes and band gaps between them, where only evanescent modes are allowed in the lattice. And for a finite type of this lattice, this translates into a high reflectivity for acoustic phonons, meaning that one can concatenate two of these lattices around a defect to introduce something that we can identify as an acoustic cavity. So most of the research in nanophononics, most of these one-dimensional lattice devices are either cavities or filters, for example. Now, one has to bear in mind that these devices are really small in their periodicity. If one really targets hundreds of gigahertz to terahertz frequencies, these periods are easily in the range of 10 nanometers or below, meaning that the interfaces have to be really, really pristine and smooth in order to avoid any unwanted scattering or decoherence. This means that at these scales, disorder becomes a relevant factor in identifying and designing these devices. Therefore, quite recently, interest from the field of phononics has been gained in adapting ideas from topology, that is, by constructing modes, resonances, based on an underlying symmetry of the superlattice or the device. One can generate a resonance and an associated spatial mode that is immune to any spatial disorder that respects this underlying symmetry that which guarantees the existence of the mode. This has been done for many different quasi-particles in one dimension. I'm just highlighting a few here, for example, for light in these coupled micropillar resonators, which host polaritons. Then in the sound kilohertz regime with these modulated hollow plastic tubes. And in our own research group, we have quite recently shown that we can extend this idea for phonons of frequencies around 300 gigahertz by embedding this nanoscale acoustic resonator inside an optical micropillar cavity. Now, this is all fine and good. However, if I am really aiming at exploiting this underlying robustness properties for an interaction, such as interaction between light and sound and Brillouin scattering, what is missing here is that this robustness has to be achieved, simultaneously achieved, for both of the interaction partners. So in my case, for light and sound simultaneously. And the essence of this talk is that I'm going to show you a platform where this is indeed possible, that we are achieving this kind of robustness for both light and sound, and as a consequence, the Brillouin scattering itself gains some robustness properties. This brings me to the outline for the rest of my talk. So I'd like to first show you the platform where we achieve this simultaneous band inversion for light and sound. Then I will go through the experimental realization of this multi-layer device and the results that we achieved by coherent phonon generation and detection. And finally, I'd like to underpin the robustness properties by a corresponding numerical study that we ran. So how does one achieve this topological protection for a mode confined between two superlattices? Well, let's start again with a single superlattice composed of, let's say, gallium and aluminum arsenide. And we have the associated band structure here. Now I start tweaking the internal structure of this unit cell. That means I am making the gallium arsenide layers thinner, while at the same time increasing the thickness of the aluminum arsenide. And at some point, I'll arrive at a situation where this particular band gap here is completely closed. By continuing to tweak in the same direction, this band gap reappears. So these two band structures here look exactly identical, with the exception of the symmetry order of the Bloch modes bounding the mini gap here from below and above. And this is exactly the symmetry relation that is maintained under certain types of fluctuations, and that guarantees the appearance of a confined interface mode when concatenating two superlattices from these two different topological phases. Now, what is the platform that actually allows this? Or more generally, what's the condition to have this effect appear for both light and sound at the same time? Well, we have to compare, to answer this question, the wave equation that governs in one dimension the propagation of light and the propagation of sound. And well, they have the same form here, with, in the case of light, here the speed of light, and in the acoustic domain, this role is played by the speed of sound. Then for a single interface, the reflection coefficient here is governed by the refractive index contrast for light and by the acoustic impedance contrast for sound. The acoustic impedance is the product of the speed of sound and the mass density of the material under study. Well, that means I have to search for a material basis where these contrasts here are equal, that I need equal ratios of speed of sound and speed of light, and ideally also equal ratios of these impedances to have this effect appear. And it happens so that this is actually given for gallium and aluminum arsenide. So these ratios here are all very, very. And if I look at these band structures with the inverted symmetry relations for the band edges of this mini gap here, I find that if I compare the band structure for phonons and for photons, they look exactly the same up to a global scaling factor, which is given the ratio between the speed of light and speed of sound. And then if I concatenate two of these lattices with different symmetries, I indeed find that I can, at least in theory, confine perfect overlap, a mechanical and an optical mode. Now, we have actually grown this kind of a structure by molecular beam epitaxy, and we have started experimentally. The first thing we did in order to identify the optical mode was a simple optical reflectivity experiment. And you see that in this broadband spectrum here, we actually identify the first stop band here, so the corresponding to the first band gap of the mini gaps, first stop band corresponding to the first mini gap, and the second band gap with a confined mode inside that is identified by this reflectivity dip here. And we see that it's at an energy, as the expectation from theory would tell us, at 1.34 electron volts with a quality factor of 2000. Now, in order to identify the corresponding acoustic mode that we claim is co-localized, we ran some coherent phonon excitation and detection experiment. That is, we are using a picosecond pulsed laser, generating optical pulses close to the optical resonance of the structure that we just identified. And we are using an intense pump pulse to generate a shock wave of phonons that propagates into the structure. And at a later time, tau, we are measuring the transient reflectivity of a second probe pulse. Then we are plotting this transient reflectivity as a function of the delay here, introduced by a delay line. And we find that we see first a very short feature here that corresponds to the simultaneous arrival of pump and probe, followed by a slow evolution over several nanoseconds that is essentially the electronic and thermal relaxation of the whole sample. And this is superimposed, you can't see it now, but this is superimposed by coherent oscillations of the confined phonon mode. And we can extract this feature by calculating the Fourier transform of this transient reflectivity curve, resulting in a spectrum with a clear peak around 18.12 gigahertz, also with a quality factor of around 2000. And this is not a coincidence. This is actually a direct consequence of the co-localization of light and sound with equal ratios of acoustic impedance and refractive index contrast for the two materials. We also ran some corresponding photoelastic model calculations that show us that this is indeed the feature we are supposed to expect. Now, the only missing element that I haven't shown you yet is to show that this Brillouin scattering interaction, or this inelastic interaction between light and sound that we are seeing here, has indeed some robustness properties due to the topological confinement that is underlying these modes. And this is actually a numerical study that we ran, where we are showing that when comparing this special topological interface mode between the two lattices, and we benchmark it against a simple Fabry-Perot resonator where we have a λ/2 layer embedded in between two equal distributed Bragg reflectors, that first, the acoustic frequency when introducing some noise. Was there a question?
No, it was just a problem with some microphone.
Okay.
Go on.
Okay, so so the first thing we observe is that under specifically chosen fluctuations that essentially preserve the underlying symmetry of the two lattices, we see that the acoustic frequency resonator is pinned at the center of the band gap, while for the Fabry-Perot resonator, we see that this robustness is essentially not present. We see large fluctuations as soon as we ramp up the spatial disorder. Correspondingly, we see that the Q factor drops. Well, this is kind of expected because we start with a band gap that is maximally open. So any type of spatial disorder will necessarily reduce locally the band gap of these superlattices and lead to a larger penetration depth, so larger leakage radiation losses from the cavity to the background material. But most importantly, when we calculate, again with the photoelastic model calculation here, the Brillouin cross-section of such kind of a resonator, we see that while the Brillouin cross-section for the topological resonator is essentially dictated by the drop in quality factor, so loses roughly 1 order of magnitude. The much larger noise in the acoustic frequency for the Fabry-Perot resonator induces a loss of the Brillouin cross-section by up to 5 orders of magnitude, even from just moderate disorder. So with this, I would like to briefly summarize the results that I've shown you so far. I've shown you that gallium aluminum arsenide multilayers are a viable platform to study the co-localization of light and acoustic phonons in a topological mode with perfect spatial overlap. And this induces topologically robust interaction between them if one studies Brillouin scattering. I'd like to highlight 2 possible routes for the continuation of this work. One is that we have recently managed to integrate this kind of 3-dimensional optophononic resonators, micropillar resonators, into optical fibers by gluing them together and studying pump-probe coherent phonon generation and detection in this completely fibered device. And the other one is that we are also working on studying these kinds of resonators in the spontaneous regime, so not in the driven pumped regime, but just in the spontaneous Brillouin regime, which opens the door to applications that are essentially based on optomechanics. With this, I'd like to thank all the people at the Center for Nanoscience and Nanotechnology in Palaiseau that have contributed to this work, our collaboration partners in Barcelona and in Paris, all the funding organizations, and you for your attention.